No, yeah. Can you hear me now? Hello?
Yes, sir.
Yes, sir.
Yes. Fine. Thank you. Now, in this graph, I would like to really impress upon you that, you see, even if you have temperatures as close as 400 nanokelvin, and you reduce that even further to 50 nanokelvin, the wave function becomes even more stronger and unified. The wave function becomes a single wave function, which is actually a overlapping of more than thousands and thousands of wave functions together. You have a single entity, and this is a new state of matter, and that's why this is called as fifth state of matter. This is a picture of a laser lab where you have multiple laser components, and the components and the lasers, the yellow color laser never gives this kind of color. This is an photo upgraded beam color. A laser will never be visible like this. So please don't get misled by these pictures in any scientific magazines also. This is shown to actually show that the path of the laser beam. Okay, when the laser beam is traveling like this, since laser beam doesn't travel in any other direction, and there are no dust particles in the room, you cannot see this. This color is added to the picture so that, yeah, viewer of the picture will know that laser is traveling in this direction. This illumination is true, the green color, because when light falls onto a wall, it's going to scatter the light, and that is real. Those colors are real, except this yellow color line that is added color to that. And this is to make things an easy way. You have hot atom, you cool, they become, as you know, that wave particle duality, the particles will also actually exhibit certain wave character, and you further cool them, they will become together and a single wave function will emerge. And once you have such kind of a character, then this is used for what is called as quantum interference experiments, quantum transparency experiments. And further, we take this to build a physics called quantum optics. Nowadays, we have something called quantum optics. And the quantum optics is going to be the mother of the idea of quantum information theory. And quantum information theory will be leading towards construction of quantum information exchange and quantum computers. I was telling you the trap. How do they cool? If this green color ring that you are seeing there, that is a glass chamber, and inside that you have multiple atoms, the red color dot. Initially they are spread over there, but there are 6 laser beams that is coming. All the laser beams are properly aligned with their phase constant, properly tuned, so that these beams will now reduce the velocity of these gas atoms. They will absorb the velocity of the gas atom, negate it. So the gas atoms will be slow. They will become slow in all directions. If the gas atoms become slow and slow, it loses kinetic energy. If kinetic energy is lost for a gas atom, it cools in its temperature. And that is how the cooling is done. It's not a traditional cooling. You have to think in a different direction. And this technique itself got Nobel Prize, as I mentioned to you. It's called laser cooling. And the magnet is required to keep them trapped. Otherwise, they'll run away from this chamber. And this is another illustrative picture only, not a real picture, how the laser beam goes and how it is going to cool. And atomic beam, as I was mentioning, rubidium beam, rubidium atoms can be thrown as a beam. This is all within the chamber, not outside. It's not a big space, very small space. So this Bose-Einstein condensate is to the matter as the laser is to the light. The analogy is precisely that simple. What does this statement actually mean? When laser was invented in 1960s, early 60s, people thought, what is the use of it? When the telephone was first invented, I'm talking about the landline telephone, it was demonstrated. Then the then president of US asked, okay, what is the use of it? Okay. When the first steam engine was invented, a trial run was made in the highlands of the present England. The local neighborhood people were telling, "Oh, this instrument is making noise. All our cattle, sheep, and cows are scary. Who wants this instrument?" That is the comment society makes. So, for telephone, I'm talking about landline telephone. Imagine now, without telephone, without such a connectivity, I'm not talking to you, you are not listening to me. Nothing is, you are not able, we cannot communicate, though we are spatially far apart, anywhere on the earth. It's the same is the story for laser. When laser was invented, the question came, why laser? What is the use of it? So sometimes there was a very remark made by many scientists. It is a solution looking for a problem. We all know that then there is a necessity that becomes the mother of invention. So we have a necessity, then we work on it. But when laser was invented, people thought, okay, what is that we can do with it? Same story with Bose Einstein condensate. We made the condensate very nice. So what? What is the use of it? And that's the kind of question that many people within the scientific community had in their own minds. But it was much later that people understood, well, a lot of applications can be there by using that actually. It took 20 years from the invention of the laser until its technological applications that took off. As you know very well, every day the lasers are there. Your CD writer, all those things, your reprographic instruments, the entire fiber optic communication is not possible without the laser. I'm now talking, the instrument is now sending message, you are able to talk back. Somewhere between you and me, there is an optical fiber, there is a laser light going. When you send a Gmail, when you send an email, when you pay something online in a computer using a bank account, somewhere a laser is there behind you. All of us know optical fiber exchange, full of lasers. So people later started using it. Similarly, the bees is also, now it has got a lot of applications. Let us see some of them actually. See some properties before that actually, how what and all it can do for us first. The fact that all the atoms have identical properties supposes that a series of determined properties can be constituted.
அதுல ஒரு ஆப்ஷன் வருங்க, லிங்க் மாதிரி கொடுத்திருப்பாங்க பாருங்க.
So can you please talking, mute yourself please. Yeah, fine, thank you. Since these condensate atoms occupy the same phase space and have same wave function, they can actually have these following properties. They can even slow down the light even to 1 meter per second. That's the very interesting property. Light travels in such a velocity 3 × 10⁸ meter per second. All of us know that. Well, it travels through water. It travels through a glass plate. It is slow, little bit slow, not very much slow. 3 × 10⁸ meter per second. And then if the light travels through a Bose-Einstein condensate, light can travel at a speed of 1 meter per second. You have reduced it to almost 1 billion times slow. That means we can manipulate the light if we are able to slow it down. And that can result in making devices, pure optical devices for the future applications. That's one of the most important properties. The other one, when I was mentioning about the helium, I was talking about zero viscosity. The Bose-Einstein condensate can also flow. These atoms can flow without friction. And they can be modulated by external fields. What is the modulation? We can apply a sinusoidal electric potential outside, and the Bose-Einstein condensate's wave function can be modulated. That means I can add an information to it. It can store the information. We can transport it and use it. It's kind of storing of enormous information. So that's the kind of properties, pure optical. That's what BEC can take us for the future. So what are the uses that are being tried, being implemented, being used, going to be used, are all being shown here. Quantum computing. Quantum computer. You type in the Google, you will find millions of returns in that. Whatever you understand doesn't matter. Quantum computing will be there in the future. The current school going children, please keep in mind, in your generation, you will use a quantum computer for sure. If not directly in your own house, at least that will be there in the usage. Quantum computer will change the way we uh, exchange information throughout the world. Every single human being on the earth will be able to have an email account. Every single human being on the earth will be able to have an online transaction without any slowness in the network. That will be possible if we have a quantum computing facility installed throughout the world. That's the goal. That's the achievement the science can provide for the humanity. And that quantum computing depends upon the bosonic properties. Very much on that. Coming to the atomic clocks, GPS, all the other things, inertial sensing, gravimetry to know where is the gas, etc., magnetometry for surveillance, ultra cold plasma. Well, we understand a little bit more, etc., scientific applications. Let us see something that which is there in our daily life. Atomic clock, world time standards, GPS calibration. Atomic clock, sir, I don't worry about it. I just Google, my watch is stopped. Go to shopkeeper, he changes my clock. It's gone. Google international time, IST time, type it, my computer keeps the time. Real, it is synchronized with the international time, it is always there. Our children are very smart in it actually. They don't depend like we people looking at the analog clock and change the needle. Well, sir, then who maintains that clock? You synchronize with the international clock in the Google, in the internet clock. Someone should be there sitting and maintaining that clock. It's not a magic that maintains it. Who is that someone? It is not a one person. It is not a single office, single instrument. It is a collection of chain of scientific instrument maintained 24 hours by 365 by thousands of scientists sitting at different places in the world, talking to each other regularly and maintaining the clock. And they actually keep correcting the standard clocks of each country. Every country has what is called as a standard laboratory. National Physical Laboratory, which is there in New Delhi, is our standard laboratory. You go to a market, you buy 1 kilogram of vegetable. That 1 kilogram in instrument is the spring balance. How do you know it is 1 kilogram? You go and buy another weighing machine in the market and check in the home. You buy 1 kilogram weigh. That 1 kilogram iron mass, who measures, who checks that is 1 kilogram? Someone should check it, right? Some inspecting officer will check it. How does he or she knows that? Who gives that data? It goes and goes. So it is a team of thousands of scientists are working day and night continuously so that I will be able to see on my computer clock standardized, synchronized. I'm having peaceful sleep because someone is not sleeping and maintaining the clock throughout the day and night. And there is a GPS calibration. We are very much happy now. Take a cell phone, GPS, where to go to travel, don't ask anybody, and then you go. That's the kind of the current travels are all about. The satellites are giving us a GPS. And how is that possible? A GPS requires an atomic clock precision, first of all. And atomic clocks can be very precise with ease of maintenance if it is going to use a Bose-Einstein condensate. Right now, people are using cesium vapors, pure cesium vapors. Cesium vapors are actually preserved in the Bose-Einstein condensate state. And that is how people try to use that action. And the bosonic theory actually helps us to maintain the density and all the other physical properties of such clocks. So the Bose-Einstein theory actually in turn helps to maintain the atomic clocks. And coming to GPS calibration, there are thousands of satellites above our head going around continuously and they guide us. We all know that actually. And this GPS synchronizes with our cell phone and helps us. And this GPS in turn depends upon what is called as pulsar. If you go and ask an astrophysicist, they will tell us. And the pulsars are there many, many light years away. They emit photons, they emit radiations, and they are measured by the satellites. They standardize it. In turn, they keep that as a reference. And in turn, they make our journey on the road here easier. Who maintain the satellites? Thousands of scientists are maintaining that. So to just keep our clock going, to keep our cell phone going, which we take it for granted on daily life, please keep in mind thousands and thousands of scientists are working behind us. Without that, we are not having the comfort. Okay, so this Bose scientific content said in the future it's going to be really a revolutionary one. Before we come to a conclusion, yeah, simple outline of what happened to Bose later, what all he did. So look at his contributions in 1947. Rabindranath Tagore, another Nobel laureate, dedicated his only science book to Rabindranath Bose. In 1942, Professor Bose became the advisor to the CSIR. All the students of science, CSIR examination, if you write clear, you get a fellowship, you become lecturership, eligibility, all those things. And 1947, after the India's independence and partition, he moved to India, the Calcutta, from Dhaka. 1945 to 48, he was the president of Indian Physical Society. In 1954, Professor S.N. Bose was awarded with the Padma Vibhushan. And 56, he was appointed as Professor Emeritus. And he also became Vice Chancellor of the Shantiniketan Vishwabharati University. In 1958, he was elected as a Fellow of Royal Society in London. And he was also nominated to the Rajya Sabha. In 1959, he was appointed as a national professor, which is the highest honor any professor can actually think of in his life. And he remained as a national professor until 1974, another 15 years until his death. And his address in the Science Congress as a president and a stamp released on his memory and recognition by Government of India in 1994. In 1986, government initiated S.N. Bose Center for Basic Sciences in Calcutta, which is a very important center. A lot of research activities do happen. Many students look forward to go there to take up research over there. And he never got a PhD and he never got a Nobel Prize. That's very important. And when someone asked him, why, how do you feel about not having a Nobel Prize? This is all what he said. I have got all the recognition I deserve. This is his own statement. I have got all the recognition I deserve. Doesn't matter whether he got Nobel Prize or not. His work has created multiple Nobel Prizes. And the explanation for that was probably because in the realms of science, what is important is not a Nobel Prize, but whether one's name will live on in scientific discussions in the decades to come. Why decades? I'm sure it will be there for centuries to come. Bosons will be there. It cannot be replaced by any other scientific terminology, and Bose will live with us forever. Thank you very much for your attention. Any questions, please?
Thank you, sir. Thank you for a wonderful presentation on history of emeritus scientist Professor S.N. Bose, the importance of bosons, and the impact of Bose and Einstein condensates. Now it's time for interaction. I request the participants to interact with the resource person. It's open to the participants, please. Any questions, please?